Well, good morning, ladies and gentlemen. This lesson is not very conducive to my whiteboard, so I'm going to try to do something a little different here. We're at lesson obviously 10.2, day one. We're going to split this into 3 days. The main thing we're going to be talking about today is up here at the top, basic exponential growth functions and basic exponential decay functions, both in the form of f of x equals b raised to the x, and b values greater than 1 for a growth, b values between 0 and 1 for a decay. Tomorrow, which I'm assuming is Thursday, May 14th, we're going to look at the compound interest, and then the following Monday we are going to look at the base e exponential function, where e is, anytime you see that little e in math, that is not a variable. It's an irrational number, just like pi. It never repeats, it never terminates, but we approximate that like we approximate pi to be 3.14. We approximate e to be 2.72-ish. And there's just a bunch more decimals going on there. If you can remember e is 2.7, you're usually pretty good. Because I don't have a fancy writing pad like Mr. Myers has, what I did was I uploaded a PDF of filled out notes, and I'm just going to try to scroll through and explain as I'm going. I don't know how many of you are able to actually write these notes, print the notes down, and take notes on our note sheets that we're giving out. But if you did, hopefully you're looking at the notes before you're looking at this, or you're looking at them simultaneously here. Our warm-up problem is basically we have Juno's opening her savings account, and she's putting in $100. The bank offers 3% annual interest, and it's to be calculated one time a year at the end of each year. And what they want us to do is they want us to write a function, a of t, to model the amount of money in Juno's savings account after t years. And up here it says, well, your bank accounts, all of your banks use this right here, this compound interest formula. It's mainly what we're going to talk about tomorrow, but just to get the juices flowing, the mathematical juices flowing, P is your initial investment or your initial deposit. R is your rate of growth as a decimal. N is the number of times interest is compounded per year. Down here, it's going to be, we're using n equals 1 because they're only calculating interest at the end of the year. And T is always time in years. So as we come along, what happens is here's our $100 deposit. 3% is 0.03. N is 1, so I put a 1 in for N. And what I did is rather than looking at it this complicated one here on the left, what I did is I just simplified it. 1 plus 0.03 divided by 1, well, that's just 1.03 raised to the t power. Or if you want to add the 1 and the 0.03 together, you could look at it as a of t equals 100 times 1.03t. Well, what they want us to do here in the next one is say, hey, how much money is he going to have in his account at the end of 1 year? That means he got paid interest one time for that year because n is 1. So all you do is you take 100 times 1.03 raised to the 1 power, and he made $3, so his account balance would be $103. If we come down here to number 3, well, now they want to know at the end of 5 years. Well, then t is 5, and it's still, all of these, he's getting paid interest one time a year, okay? Monday we're going to look at, or actually tomorrow we're going to look at what happens when n is not 1, like your actual bank account is right now. But at the end of 5 years, all I have to do is take 100 times 1.03 raised to the 5th power. Well, that gives me, you type the stroke there right into your calculator as you see it, $115.93 would be in the end of, it would be in his account or her account at the end of 5 years if they made no further deposits. And at this rate, at 3%, which is a really super high interest rate for a savings account, don't think you're ever going to get that much. How long is it going to take for her initial investment of $100 to double? Well, basically, I kind of have this all written out, and all I did is I took, okay, my account balance over here, I want to be 200 when my initial deposit's 100 at 3% interest raised to the t power. So as I solve this equation, the first thing I would do is divide both sides by 100, and then I get down to 2 equals 1.03 to the t. Well, the only way you're going to be able to solve this at the time right now is to use guess and check or graph and solve it, because to algebraically solve it, we need logarithms, and we didn't really teach how to do that yet. That's actually the next chapter. So what I did here is I'm going to come over here to my calculator, is I graphed my 100 times 1.03 to the x, and then I graphed when does it equal 200. And what I did was is I find the point of intersection. When is the red and the blue graph the same? Well, they are the same. They are both 200 at 23.4498. So that's why when I look back here at my answer, it will take more than 23 years to double. If they are getting paid interest one time a year, okay, it's going to be at the end of the 23rd year, the beginning of the 24th year, when she gets paid her interest, that she would actually have her amount doubled. Okay. Now from here, see if I can squeak in there, go to my next page. Okay. Typically, what we usually do with this is usually partner or groups of 3, and we do a matching thing here, and you're going to have 6 graphs in there, and we're going to match the exponential graphs with their correct equation. I'm going to sort them by growth and decay first. Then we're going to complete the table associated with each equation. Well, I have this all done, and if you remember back to Algebra 1, okay, exponential growth function, as you read your graph from left to right, grows. So graph A is a growth function because it moves from left to right, and it goes upwards from left to right. Graph B is a decay function because left to right it goes down. And C is again a decay, left to right it decreases or decays. Graph D is a growth. Graph E is also a growth. And graph F is a decay. Now notice all of these. When I look at my growth, here's a growth, here's a growth, and here's a growth. A, D, and E are all growth functions. Notice they are all growing at different rates. One is much steeper than the others, and one is much flatter than the others. And the same thing goes on with my decay functions over here. And what we're going to be investigating is what value is it in our equation that actually dictates how fast or slowly something grows or decays, okay? So there's my graphs, and when I'm looking at my growth functions here, okay, this one grows really fast, this is the slowest growing, and this is my medium growing. If I think of large, medium, and small fry in terms of growth, what we're going to actually do is we are looking at these growth functions here now. So this is just a little awkward here for me in here. And what we're looking at is I have the functions we have. F of x equals 3 raised to the x, 10 raised to the x. And let me get this last little squirrel opened up. We have 1.5 to the x. Well, I can figure these out. You know, I can plug these values into my equation to fill out this t-chart. And no, we do not need a calculator to do that, because when I plug -1 in here, well, 3 raised to the -1 power, remember that negative exponent actually turns it into 1/3 to the positive first power, which is a third, okay? So that negative exponent just flips whatever it is over. Well, as we're looking here, okay, 3 to the x, 10 to the x, and 1.5 to the x, well, steepest growth, notice that 10 right there is the biggest number, therefore it's going to be the steepest, fastest growing, because when I raise 10 to powers, it grows faster than when I raise 3 to a power, which is even faster than when I take 1.5 and raise to a power. So because my b value here in f of x equals 10 to the x, because my b value is the largest of these 3, that one is going to be my steepest function. When I'm looking at right here, f of x equals 1.5x of my three growth functions. That is the smallest b value, therefore it will be the slowest growing, which is graph D, which is right here. It's not as steep. And the 3 to the x is kind of in the, well, it's not in the middle, but it's between those two. It doesn't grow as fast as graph A and not as slowly as graph D. When I'm looking at my decay functions, basically the same thing goes in there. Everything banks off of my b value. When I have f of x equals 1/3 to the x, when I have f of x equals 0.1 to the x, and f of x equals 2/3 raised to the x. Okay, think about this. If I look at 0.1 is actually 1/10. So that is the smallest number, and because it's the smallest number, it will be the steepest decay. Because this number here, 0.1, is smaller, it's going to decay faster, meaning 1/10 of whatever I started with is left each time I raise it to a power, where up here I have 1/3 is left over each time, and down here I have 2/3. Okay, so what I'm looking at is graph B right here. That's my steepest decay function. It goes down the steepest because my b value is the smallest. And here, graph F is my flattest decay function, which is going to be my biggest b value. Okay, so it's just kind of flip-flop between growth and decay. 2/3 is there, and the way I always think of it is the number that's closer to 0 is going to be a steeper decay graph than the number that is closer to 1 will be the slowest decay graph. And 1/3 falls between 1/10 and 2/3. Therefore, it is the medium fry right here, or graph C. Hopefully that makes a little sense. Usually we would have given you about 15 minutes to match those all up in class. And now I think I'm on to my third page here. Well, analyze those exponential growth and decay functions from the previous page, okay? We're looking at all six of these, functions, and there is something all 6 of them have in common, okay? And as you're looking at all these, what do all 6 graphs have in common? Well, what all graphs have in common, and for the examples of all these today, remember the essential idea says we were looking at f of x equals b to the x. Well, the general equation for an exponential is a times b to the x, but all these equations we're looking at today, the a value is 1 for every one of our graphs. And as we're looking at those, what points did they all have in common? Well, they all had the exact same y-intercept. They all went through the point 0, 1, which, see, 0, 1 on all 6 of these graphs as I go through. Well, there's a specific reason for that. The reason they all go through that is because when I take b raised to any power, when I put 0 in there, anything to the power of 0 is 1, okay? So that's the reason. Any base to the power of 0 is 1. Anything to the 0 power is 1. It is not 0. And then we're moving right along down here. Compared to the equations of the 6 graphs you sorted, well, what generally differentiates growth from decay? It is exclusively that b value, okay? And a growth function, the b value is always greater than 1. So whenever you're looking at an exponential function and whatever is raised to the power is greater than 1, it's going to grow. And whenever that b value is between 0 and 1, it is going to be a decay function, meaning left to right it's going to get smaller, okay? Now, what they want us to do is with a graphing calculator, which I have all these, I graphed all these, okay? We're going to say, why does b have to be greater than 1 or between 0 and 1? Why can't b be 0? Why can't b be 1? And why can't b be a negative number? And here is why, okay? If b were 0, what we would be looking at is an equation y equals 0 to the power of x. Now, when I put in 0, 0 raised to the 0 power, contrary to what you may think, it is not 1. That's actually undefined, and it's undefined. It's upper level concept that you would talk a little bit more in calculus about. But when I graph that, it's actually a constant function, but only for x values that are greater than 0. So what the graph is going to look like, I'm going to show you, it's going to look like y equals 0. Except it's not going to be y equals 0 all the way across. It's only going to be when y is greater than or equal to 0. So if I come over here to my next graph, here it is. And I can see when I highlight that, notice that pink graph does not go into the negative numbers, because remember, what does a negative number do? What is 0 raised to the negative 1 power? Well, that is the same as 1 over 0 to the first power, which is undefined. And we don't know what it is. That's why my graph only goes to the right in this case. Then we're going to say, well, how about if b is 1? Well, think of that. That's a pretty obvious one. Well, if I raise 1 to any power, I get a constant function. 1 raised to any power is 1 all the time. That is going to be the equation y equals 1 for all x. So that's just going to be the horizontal line of y equals 1. It doesn't grow, it doesn't decay, it's just constant all the way across, because when I take x, when I raise 1 to a power, I get 1 back every time. Now the crazy one over here is, what happens if b is negative? Well, if b is a negative number, I don't care what negative number it is, if a number is less than 0, it's negative. And whenever I'm raising something, a negative number, notice there's parentheses around that negative number. Whenever I'm raising a negative number to a power, what I get is an oscillating function, because whenever that exponent is an odd number, it's going to spew out a negative number. And whenever that exponent is even, when I raise a negative to an even number, it's always a positive. So this isn't going to give us an exponential graph at all. It's actually going to give us an oscillating function, which it's a really wonky looking dude here. Looks kind of like that. It oscillates from positive to negative every time it goes back and forth, and it bounces up and down, and does not reflect exponential growth. Remember, growth is either going to go left to right, it's going to go only up. Decay is going to go only down, and this does neither. So it's not even an exponential function at that point when x is negative, or when b is negative. And moving right along, write an exponential function. So we're just going to write 3 of these. And now I did put a note here. A is 1 for everything today. Y equals b to the x with the given characteristics. Well, here's my characteristics. Increasing from negative infinity to infinity. So that's left to right. That's all the way from the left all the way to the right. It's going to increase. Well, that means I have a growth, because it's going to look kind of something like that. And if it grows left to right, that means my b value has to be greater than 1. Well, not only is it growth, I'm going to have a reference point. The graph that we're writing, or the equation we're writing, has to go through the point 1,6. Well, if I take my general formula that they gave me up here, y equals b to the x, and I actually plug in my y value, I plug in my x value to find out what b is. Well, b to the first, what to the first power gives me 6? Well, b has to be 6. So my equation would be y equals 6 to the x. If I took my next one here, well, I'm decreasing from negative infinity to infinity, so that means it's a decay. If it's decreasing, which means left to right, it's going to fall. Well, that means my b value has to be between 0 and 1. Well, I'm going to do the same thing. I'm going to take my y equals b raised to the power of x. I'm going to plug in my y. I'm going to plug in my my x. And remember, b raised to the negative 1 power, well, that's like 1 over b to the first power. I could multiply both sides times b and then divide by 4, or think, well, if I take the reciprocal of 1/4 to the negative 1 power, oh, that's what 4 is. That's why b would have to be 1/4. So this would be y equals 1/4 to the x. If it's a decay function, b has to be between 0 and 1. And moving along here, end behavior, they're telling us our information just a little bit differently here. They're saying, hey, here's my end behavior. When as x approaches negative infinity, when I'm way to the left, my graph is 0. And as I get really big x's, my graph goes up. Hey, that means it's increasing. So it's going to go from 0 and it's going to go up. So that means it's going to be a growth function like so, which means b is going to have to be larger than 1. Well, I'm going to do the same thing. I'm going to plug my y in for my y, my x in for my x, and I run into 6.25 equals b squared. Well, you know how to solve that. All I'd have to do is take the square root of both sides. Typically, we have a plus or a minus whenever we square root. But when we're talking about an exponential function, okay, the square root of 6.25 is 2.5. If it's going to actually be a growth or a decay function, b must be positive, so I have to take the principal root or the positive root there. So b is 2.5, so my model would be y equals 2.5 to the x. And summarize the characteristics below. Well, basically what we want to do is we are summarizing what are the characteristics of a growth function. Now notice, this function never went below 0 in this case. Okay, there's no way to raise a positive number to a power and get a negative number. There's no way to raise a positive number to a positive exponent and get 0. All they can do is get really slow or really small. Okay, so as we are looking at these, get back to my notebook, and as I'm looking at this little bugger, well, we're looking no a value here for y equals b to the x, a basic exponential growth. Well, the domain. We can put anything we want in there. We can raise a positive number to any exponent we want. We can put negatives in for x. We can put positives in. So the domain goes negative infinity to infinity, or you can call it all real numbers. The range. Well, taking a positive number raised to, I don't care what exponent it is, if it's positive or negative, the only thing you can get out is a positive number. So the range has to be all real numbers greater than or equal to, not equal to, excuse me, y, all reals greater than y greater than 0, or we can say from 0, not including 0, to infinity. Notice both of these exponentials, they do have a horizontal asymptote. They get snug as a bug in a rug down to 0 in this case until we start shifting them with transformations, which we will. But the parent function always will approach 0. How will it approach 0? Well, that'll show down here if it's basic growth as x approaches negative infinity. So when I'm way to the left, it's approaching 0 from the top. That's why I put the little plus up there. As x approaches infinity, or as x values get really big, the graph grows really big. Okay? Intercepts. Well, it doesn't, the parent function doesn't touch the x-axis, so all I have is a y-intercept of 0, 1. And I do have a little note in here. As soon as we run in and we get away from the y equals b to the x, and we're talking about y equals a times b to the x, well, now my y-intercept is going to change. It's not going to be 0, 1. It's going to be 0, whatever that a value is, because this b to the power of 0 is going to turn into 1, so I'm looking at 1 times whatever that a value is to get that y-intercept. And behavior I already talked about there. And intervals of increase and decrease, well, if it's a growth function, if it's an exponential growth, it is always growing, meaning it is always increasing. So the interval in which it increases from negative infinity, so that as you're way to the left, as you move to the right, that graph is going to gradually get bigger and bigger. And when you're looking at it way out to the left, it grows really slow until you hit positive exponents, then boom, it shoots off and it goes up fast. And this is just y equals 2 raised to the x power. When I look at a decay function, when that b value is between 0 and 1, well, that just kind of flips my graph from left to right now. It starts big, and then it gets really small. Notice it has that horizontal asymptote. It's going to approach y equals 0. It's going to approach 0 from the top side. So as I list out my characteristics of a decay, well, again, b is a number between 0 and 1. I can raise that to any power I want, so the domain is all real numbers again. The range, when I take a positive number to an exponent, don't care what the exponent it is, I have to get a positive number out, so that's why it's always greater than 0 or 0 to infinity. Has that horizontal asymptote of y equals 0. has the basic y equals b to the x graph, parent function, has a y-intercept of 0, 1, but when we change it to y equals some number times b to the x, that y-intercept is going to be 0, comma a, because again, this right here is going to be 1 times whatever a is. Now, exponential decay. As I come from the left, as x is really, really small, way over here to the left side, well, it's coming down, so it's a really big number. But as x gets bigger, as I move to the right, my function will come down to 0 from the top side. And if it's a decay function, that function is always decreasing, so it's going to decrease from negative infinity to infinity. We'll take off from here tomorrow. Have a good rest of your day.